Okay, it's recording. All right, so we're going to start and look on page 44 through 47. We're going to review the skills. At the end of class, I'll tell you, you'll have a chapter test on chapter 1 that you'll finish, and then we're also going to do work beginning in chapter 2. Okay, so if you'll turn to page 44 at the bottom, and we're going to look at R1. In fact, let me change it just a little bit. I'm going to go down because I've got some information here. All right, whenever you're doing an absolute value dual inequality, all right, whenever you have the absolute value marks, whatever this is, whether it's positive or negative, it was changed to positive. That's why this answer is positive. But when you solve it, you copy that sign over here and you put the negative on the other side and you work all 3 parts. And almost everybody in here is good at that because I really tried to stress that last year. Okay, so, but what happens, depending on this sign, like for instance right here, when you're done, this will say x is less than. And so you're going to start down this way. But then the one over here will say x is greater than, and that's going to come this way, and so you'll be on both of them at the same time. All right? If this sign were flipped and it said x is greater than, that would be this. And then on this side it would say x is less than, that would be this. And so whenever you have a dual inequality from an absolute value, one of these 2 conditions will be the graph. And you should be able to figure it out fairly quickly, but it'll be one of these 2 conditions. That's something you need to bank into your memory. That when I do the absolute value, now what's the absolute value look like when you look at it as far as the graph is concerned? It looks like a V. Right, and let's say that I'm right here. I've got, as I go this way, the graph is going positive. And as I go this way, the graph goes negative until it reaches this point, and then it goes back positive again. All right, so the graphing of it will look like that. On the number line, the values will look like this or like this. Okay? All right, so now we're going to talk about domain and range. All right, for your notes, domain, range. Domain and range in your notes. You should already know this, but it is extremely important in Algebra 2 that you recognize domain and range. All right. Domain are values of x. They are the input. Range. Values of y. It's the output. All right, now, one of the things that we're going to do is that, let's say that I give you a squiggly graph that looks like that. And that it is in this area here. What is the domain? Again, what is domain? Values of x. So the smallest value of x is right here, and the largest value of x is right there. And so x will be greater than this value, and let's say that it's 1, and it will be less than this value, let's say that that's 5. All right, now you see how these things are beginning to relate? Okay, so the x for this particular graph is in between 1 and 5. Now, so that's the domain. is the set of x's such that x is greater than 1 and less than 5. All right, now what about the range? The range is up here at 3 and down here at -2. So the range is the set of y's such that -2 greater than y is greater than 3. Okay? Now, the notation we're going to see in one of our chapters. But the reason for it is that you're going to, as a test question, you're going to give the domain and range of a squiggly graph that looks like that. Okay, so any questions how I got the values of 1 and 5, -2 and 3? Any question on the values? Just look them up on the correct axis, right? Now, the domain is involved with which axis?
The x-axis.
The x-axis. That's why domain and values of x have to be pretty solid in your mind, in your memory. And the range is talking about the y-axis and the y values. Okay? All right, so now let's say that I had one up here. All right, what would you be doing to be able to give me the domain of that one?
You'd start on the negative side.
Yeah, right. The domain would be that x, let's say that's -2. That -2 is less than x, which is less than
5, which I think is that one.
it looks like 5 again. Okay. Less than 5. And now, what you do with this for notation. All right, you have to have a set. So I'm going to have set lines on either side, and I have to tell which it is. All right, the domain is the set of x's such that. So the domain is the set of x's such that -2 is less than x, which is less than 5. Close the bracket. And the same thing would be true for range. All right, in this case, the range is the set of y's such that. Now, last year, I had more trouble getting students to buy in to writing that notation. What they gave me was just this part. They gave me just that part. Now, is that correct?
No.
Maybe in its basic form, but it's not showing a high level of Algebra 2 understanding. Okay? So that's the reason that the other part is how I'm trying to teach you so that you get those values set up in the correct notation. All right? And then when you see it, you'll also be able to read it. Okay? All right, so that's domain and range. We'll come back to that in a bit. Okay, Katie properties. All right, what's the name? Commutative. Associative. Distributive. Identity and inverse, or inverse and identity. I don't care which one you do. All right, then you have the multiplication property of -1, multiplication property of 0. Then you have the properties of equality, adding property of equality, subtracting, multiplying and dividing properties of equality, and then you have reflexive, symmetric, transitive. Reflexive is x equals x. Symmetric is if x equals y, then y equals x. And transitive has the three of them. If x equals y and y equals z, then x equals z. Okay, so, all right, those are all the properties. And I'll talk about those. You're supposed to know these. Hopefully that it was a refresher for you to go back on these properties. Actually, there's 4. But again, I made up that Katie list. Oh gosh, probably about 1994, something like that. And so I've been using that for a good while, and to me it helps put it in a package so that you get those. Okay, so those are things we had a test for that. Okay, so now we're going to talk about the review. Now turn in your book, page 44. Now we're at R1. R1. Okay. Now it asks you to. For the first one is get a rational number that's not an integer. Right. So basically, what we're looking for is any fraction that does not produce a whole number. Right? So as long as the two numbers are different and it's a fraction, if it's a fraction, it's rational. Right? And as long as it doesn't come out to be a whole number, you're okay. Now, that's not the only way to write it. You could write it as a decimal. Right? And if it had a decimal part, could you write it as a mixed number? Yes, you could. But the easiest way is to write a fraction where the numerator and denominator are different, and you'll have a rational number that's not an integer. All right? An irrational number that is not positive. All right? To have an irrational number, the majority of the time, you're going to work with a square root. You're going to work with a square root. That would be the irrational part. And if it's not positive, what does that mean?
Negative.
It's negative. To be able to show a negative on a square root, you have to have the negative sign in front of it. So this has to be non-perfect, so I'll take 15 instead of 16. So negative, the square root of 15, is an irrational, non-positive number. If I had had a cube root, would that have worked?
Yes.
Sure, cube root would work, but this cube root, I could have had negative 15 in here because I want a number that's multiplied by itself 3 times and ends up at negative 15. Get your calculators out, find out what that is in 4 decimal places. Yep, we got it. Okay, now, all right. Okay, all right. Wait a second. All right. Okay, I want to go. Oh man, isn't that cool? Move right here. Okay. Once I erase this. Okay. If you had .333 repeating, I've already taught you this. How do you find the fraction of that? You do math frac. Remember that? Okay, so let's do this. Start here. Clear your calculator. Put in 2 divided by 3. Press enter. You get 0.666666. Why do you have a 7 on the end?
Because they rounded it up.
Because it's rounded. Okay, now, if you want a fraction, you press math frac, number 1. Then when you press enter, it takes it back to a fraction. Okay? Now, go back to math. Look at number 4.
Oh.
So press 4, and now you have the cube root. Now put in negative 15. And when you press enter, you got the number. All right, so in math, now let's go back and look at math. In math, you have a cube as number 3. So the x squared is on the outside, right? So if you had a number and you wanted to square it, the cube is in math, and so is the cube root. So you got math frac, which we'll use, and then you also have number 3 and number 4, which we'll use. Number 5 is using for roots that are more than that, but we've got an easier way, and that is to use the caret on the outside. Okay, so, in fact, let's double check that again. If you needed 3 raised to the 5th power, in the calculator, go exit out, go quit, second quit, and clear. All right, clear, get a blank screen. All right, if I want this, I'm going to take the number 3 and then raise 2, which is above the divide by sign, and then 5th power. All right, now, the newer calculators automatically put it into the exponent form. The older calculators will have the caret there, and what you'll see is this, 3 raised to 5. Right? The newer calculators automatically move it up, and so when you press enter, you're going to get 243. Okay. Right now, later on, because we're getting out of using quadratics and squares, and we're going to be in cubes and some higher numbers, that may be helpful for you to know. Okay, so math, now we have math bracket number 1, and then we also have a cube and a cube root at 3 and 4 that you can use to help the calculator help you. Okay, so that was a little diversion, but I think a good one. All right, now, imaginary number. What's imaginary?
One that does not exist.
It's not real. So when you take the root has to be positive. An even root of a negative number will be imaginary. So I could give you, if I wanted to be really cool, I would give you the 4th root of -7. Now, normally what would you do? Square root of some number, right? But any even number root will produce an imaginary number, because if I have 4 of those negatives, I'm going to end up with a positive. I can't get a negative with 4 except an imaginary system. All right, okay, transcendental number, there they are, write them down if you need them. You won't need them after this chapter. Except to know that pi is transcendental. The rest of them you don't get till you get in triple. Negative even number, what did I say?
That's one that I do know.
I'm sorry, can you please tell us again?
And then our positive number that's not a digit. Digit by definition is 0 through 9. So a positive number is any whole number. Well, actually it says positive number, so it could be a fractional part too. So it's any number except one of those digits. A natural number is a counting number that does not include 0. And then a real number that's not a natural number is going to have to be 0 or a negative number.
Mr. Belcher?
Yes.
Is it supposed to be 3.1?
I'm sorry. Say again?
The pi and the transcendental?
Say the question.
Is it supposed to be 3.1 or is it 3.2? Like, look at the pi.
No. This is not pi. You see that little mark on there on the top?
Yeah.
That says that this is a highest integer sign. So it says, take whatever fraction.
It says no.
I've got a timer on this. Take whatever fraction you have and raise it to the highest whole number.
Oh.
So this would all be raised to 3.
Okay.
Right? No, I'm sorry, it would not. No, if it raised the highest, this is more than 3, so this would be 4.
Okay.
Right? And if that little mark is on the bottom, then it goes down. Right? And so, but again, that's called a transcendental number. So that was not trying to be, in fact, I'll tell you what I'm going to do, just to be able to keep that from being a problem. That'll solve that problem. Okay? All right, now, so that takes care of all of those, I think. Okay, an irrational number that is not real. Okay, now this is interesting. An irrational number that is not real does not exist, because all irrational numbers are real. And again, that's a trick question. Okay? Okay, now, what I did for 1B, and 1B says, tell which of the groups of numbers are related to these particular problems. And so what I did is I put a thing across the top for digits, natural, whole, integer, rational, irrational, real, imaginary, complex, which is part of imaginary, transcendental, and negative numbers because they asked for negative in there. So if you see 2, because it's positive, it's a digit, right? It's natural, it's a whole number, it's an integer, it's a rational, and it's real. All right, it's not negative, so that's not it. All right, if I have negative 3, negative 3 is not a digit. We don't count down in there, so it's not that. It's not a whole number, because the whole number starts at 0 and goes positive. But it is an integer, and it is rational, and it is real. And it happens to be negative. All right, so those are the answers to those. I don't think too many of those were very hard, and the test you're going to have is not going to be that difficult on that part. Okay? All right, now, R2. All right, I have written these down for you. We don't spend a lot of time in this one because we don't do proofs. We don't spend a lot of time on this, but if I were a student and I were sitting there and somebody were to say, those are the answers to 2A, what would I do as a student? I'd write them down in your notes.
Do it.
Duh. Okay. Yeah, write those down in your notes. Again, we don't spend as much time in our Algebra 2 class on those things because we're not doing proofs. If you remember chapter 3 in Algebra 1, we went through it very quickly where that's a long chapter to get to do that right. I didn't even know what a lemma was.
I didn't know it existed.
Or a lemma, I guess it would be. See, I always call those axioms, but axiom is accepted and it's used to prove another property. Right, corollary I didn't know, and hypothesis. Hypothesis comes out of science too. The problem is that these questions are not on your test. So you got them in your notes. Okay, here's 2B. The definition of subtraction is a property, it's not an axiom. The multiplicative inverse property, inverse, right? That is an axiom, and it can be used to prove other things. The trichotomy, something is either greater, it's less, or it's equal, right? That's an axiom because it's used to prove other things. Closure is an axiom. The additive identity property is an axiom because it can be used to prove other things. And the multiplicative order is not an axiom. And then you don't have to do 2C, but I want to show you that just for example purposes. All right, this is an example of what the extra credit project. You're going to have an extra credit project on your test, and it's going to be asking you to do this. You're going to write this property, this is given. Okay, now, this was changed to this. Why? Because that's the definition of division. Then I changed this to this. What gives me the right to do that? the multiplication property of -1 says that -1 times x is equal to -x. So negative y is equal to -1 times y. That's the multiplication property of -1. And then now I change this into this. Right? That's the reciprocal of a product, which is what the book says. But you could also say that's the definition of division. I have this number divided by this number. This number divided by both of those is what that is. All right, and then what happened here? This was changed to this. It's either a number fact or it ends up being the reciprocal of -1. -1 is the same as 1 over -1. All right, and then this parenthesis was changed from here to here. That's associative property multiplication, etc. going down. All right, again, in Algebra 1, we have a whole chapter 3 that does that, but because we weren't doing proofs, we just went over it really quickly. All right, there's going to be that's going to be the extra credit project for your, oops. And then eventually you get all the way down to here, and this first one is equal to this one. That's the transitive property. That'll be the last one. Okay, and I went over that quickly. Now, we've already done the quiz of the properties, so we're not going to do that. Okay, this is going to be the assignment for this week. We're going to go over 2.1 through 2.4, and you're going to do the Chapter 1 review. We've already got that done. So you're going to do the chapter test 1 through 8. So turn over to page 47. All right, and the assignment that you're going to have to turn in next week is the chapter test 1 through 8, and then 12 is an extra credit. So 1 through 8 has several parts. Please identify what answer to what part, like 1A, 1B, 1C. Please show those answers so that I can read it better. Okay. This will be up on the teacher page. It's also up right from the website, except for week 4. Okay. All right. So. Right here, and I got, please indicate on your paper the problem number and letter. All right, that's just very helpful for me. All right, any questions about chapter 1? It should be straightforward. We just want to get out of it and move on. Okay? Right. Okay, so now we're going to talk about chapter 2. I've already started it. Okay, let's turn really quickly to page 52. All right, on page 52, this is a review of what an ordered pair is. All right, it says the ordered pair is 9, 1. Which one, on page 52, problem 1, which one is the x?
9.
The 9. Which one is the y?
1.
The 1. So in that equation that says 2x minus 3y equals 15, what are you going to do with the x? You're going to substitute 9 for the x, you're going to substitute 1 for the y and make sure that it works out. Okay, it should equal 15. If it didn't equal 15, then what does that tell you about the point? And this is important.
The point is incorrect.
Then the point is not on the line. The point was correct because I gave it to you. Right? But the point is not on the line. So here's what I want to, in your notes. If false, point is not on the line, and later on we're going to find that line and graph are going to be the same thing. All right? So if it's false, then the point's not on the line. Now, what we'll do later on in the course is that suppose that it's bigger. that the answer that you get when you substitute, like this one here, if it's equal, it equals 15. What happens if it's less than that? Suppose it's 14. Then that means that it's under the line. If it was 17, it would be over the line. And so that will get us into inequalities, right? Okay. But for the purpose of what we're doing, if it comes false, it means it's not on the line. All right? Now, all the rest of that is just following directions. Okay, now that gets us into 2-2. All right, turn to page 55. Does that look familiar? Did we go over that? All right. So that was the graph. If I give you a weird looking graph, all right, you've got to find out where the y values are. That's the range. And find out where the x value, D-O-M-A-N, that's the domain. Okay. Now later on we're going to get to intervals. Have you heard the term interval before? Okay. Interval is related to the x-axis. And what it's going to look like is something like that. Now, it could have been 2 parentheses, and then the first time you see it, you think it's a point on the coordinate plane. But if it's an interval, does it touch -3? The answer is no. It's open on -3, and it goes here, and it's closed on 5 because that's a brace and the other's a parenthesis. Okay, so if I had that over here, let me turn this. I'd have it open in here and closed in here. So my interval starts at -3, but it doesn't include that point, so the circle's open. And then the highest part is +5, and the circle's closed, so it includes it. And the interval for it would look like that. Intervals are only for x-axis. Right? And so then the question is, how do we talk about it? All right, that gets back to the range domain set such that. Okay, so let's talk about it, because it's on the next page, I believe. Yeah, bottom of page 56 is where we're going. So we're not yet at intervals. That won't be till the other half of the year. So we're going to talk about the domain is. All right, write this in your notes. The domain is the set of x values such that. The set of x values such that, and then here is where your expression is going to go. And then you're going to close the parentheses. All right, and in the one that I gave, we said that x was, or -3 was less than x, which was less than or equal to 5. That would be the expression. And now, because we're in Algebra 2, those inequality signs don't have to be the same. Many times they are, but they don't have to be now, because we're smart enough to understand that the graph could look differently. Okay, does that make sense? All right. So that's what we're talking about here. That we're going to define the domain is the independent variable, and that'll become clear in a second. All right, now what about the range? What am I going to put here? Everybody?
Y.
R, not Y. Range. Range equals set. Now, Y such that. That's what you have to learn this too. And as I said, last year I had a lot of problems getting my Algebra 2 students to be able to buy into learning this and before you put the expression in. And so then I might have something like this. Y is greater than -3. Right, that would be fine. You don't have to have a dual expression. You can have a single thing. Right? And what does that mean? That means I have an asymptote right here, and all my y's are above that. So it might be something like this. Okay, make sense? A little bit? All right. Okay, so those are domains. All right, now, the other part that I've got in my notes that I want to take a second to talk about, and that is direct and indirect. Okay. Direct variation is a math term for a specific problem. Right? And in a direct variation, y is equal to k times x, or y is equal to kx. K is a multiplier. And in order to be able to get a problem that's a direct variation, I give you the relationship of the x and y. You have to find the k, and then I'll give you another y, and you have to find the x, or I'll give you another x, you have to find the y. So let's say this, that in direct variation, when x equals 4 and y equals 12, x varies directly with y. That's the first statement. Okay, now, with that information, what does k have to be so that 12 equals k times 4? K has to be 3, right? So therefore, the equation that we're working with is y equals 3x. Right? Now, that is gotten by understanding what x varies directly with y means. If you don't understand direct variation, you don't know what to do with the 4 and the 12. Right? Then, what is y when x is 10?
30.
30. But again, you're not given this information at all. If you try to do this with proportions, 4 is to 12 as 10 is to x. Oh, 10 is to y, sorry. 10 is to y. Will that work? If I did proportions?
No.
Huh? Well, if 4y equals 120, how much is y? Get your calculator out, people. If you cross multiply, right, you have 10 times 12 divided by 4. And the y ends up here.
So it's 30 still.
It's still 30, right? So you could solve that proportionally if you understood. Right? That's direct variation. Okay. Right, is that in your notes? Right, that may help sometime later. What in the world's happening here? Okay, now, 2-3. 2-3. Turn to page 62, and I'm going to be sitting down for this. Okay. On page 62, first thing that you need to know is that time is usually independent. Time is independent. Write that in your notes. Time is independent, so time will be an x-axis most often. Okay? Now, what this page of sentences is a situation that you are supposed to change into a graph. If you remember, in the last section, we had a squiggly graph and we showed that the domain was between this interval and the y had a range in between here and here. Okay, well now we're going to create some of those graphs. All right, and this is not simple because you haven't done this. All right, and so what we're going to do is we're going to discuss those, and this is that little half sheet. So let's look at the first one, the first problem. It says the distance you have gone depends on how long you have been going at a constant speed. So what happens before you start? How far have you gone?
That'd be distance.
You have the distance would be 0, right? Okay, so on the y-axis of problem 1, really small, write the word distance. So you have distance here, and then you have time here. See on your handout, problem 1? All right, I put time on the bottom, but the y-axis is distance. Now, what happens as time goes by? The longer you are walking, what happens to the distance? The farther you go. And the parenthesis says you're going at a constant rate, therefore the line is changing as a straight line. All right? And so that becomes the graph of problem 1 as a sketch. Okay? Now let's look at problem 2. The number of used aluminum cans you collect and the number of dollars refunded to you are related. Okay? What happens if you collect no cans? Then you got no money, honey. Right? And so therefore this is going to start at 0, 0. Right? And it assumes that the cost per can is the same. Right? And so that's a constant change. And so what's going to happen? The more cans you have, the more money. And so in this case, what will be the y-axis? Money or dollars. Yeah. Money or dollars will be the y-axis. All right? Now we get to number 3. Number 3 says the distance required to stop your car depends on how fast you are going when you apply the brakes. Okay, now, if you're barely moving and you apply the brakes, how long is it going to take you to stop? Almost no time at all, right? So this is close to 0, 0, although if you wanted to raise it up a bit and not be at 0, 0, that probably would be right. And then the more speed, the higher the y speed, the higher the x speed, the longer it takes to stop, right? But it's not constant in most cases. In most cases, the speed, and then you get to a place to where you can't stop at all because you're going too fast, right? And so anyway, but as a graph, it's going to have a curve in it. Okay? Same thing with number 4. The mass of a person of average build depends on his or her height. Now, does that have to be at 0, 0?
No.
No, because usually a baby weighs what, 7, 6, 8 pounds, something in there. Right, and so even at birth, it may not be at 0, 0, but it goes to a certain spot. But then what happens? Does the height keep on going?
Yes. Well, the
How
height doesn't keep going.
See, no, because we have some other things, so that there may be a limit to how high that is, and that may actually cut off and then say that like nobody's over 8 foot tall, although there might be. Nobody's over 9 foot tall. right? But there may be an upper limit to that. Okay? Now, let's go to number 6. The altitude of a punted football depends on the number of seconds since it was kicked. All right, now, in number 6, why did I start that in the middle of the y-axis? Oh, by the way, what's the y-axis on that one going to be?
Altitude.
All right, look at number 6, altitude. What is altitude? Starts with H.
Height.
It's height, right? So you can put height or altitude. But why did I start that in the middle?
Because it doesn't start at ground point. It starts.
Because when you punt the ball, it's not on the ground. The ball's actually in the air when you punt it, right? So it starts there, and then what's going to happen? It's going to go up, but then gravity is going to take over, and then it's going to come down, and then it's going to hopefully, unless somebody catches it, it's going to hit the ground and then bounce up, and then maybe come back down again. And so that's what I tried to show. That's the graph I tried to show in number 6. Okay? All right, now, so your assignment is to do problems in this section. You're supposed to do 2 through 12 even. Okay? All right? Okay? All right, so that's going to be the discussion for those sections. All right, now, if you will, turn to section 2.4. I'm going to double check. Yeah, we're only doing part of, we're doing 2 through 12, and then we'll pick up and talk about some more of those next week when we move on. Okay, now, all right, I'm going to make this larger so you can see it. How's that? Is that better? Okay, now, in the first graph that says constant, it says y equals some number, y equals c. And now, this particular chart says f of x. All right, now, in function discussions, f of x is y. And you should know that. The reason that it's put f of x is that if you are wanting to know the value of y at a particular point on the graph, I can make a notation. And the notation would be this. Yeah, that says f of 7. This says replace the x with a 7 and tell me what the function is. Now, I didn't give you the function, so you don't know. But let's say the function was this. Let's say that f of x was 2x minus 11. So, what happens in this function of f of x when f is 7? What is 2x minus 11 when x is 7? Okay, now, you don't have to do that in your head because you have a tool on your desk. And so, what would you put in the calculator? Gavin, what would you put in the calculator? 2 times 7 minus 11 and get what the answer is. Right? And what is the answer? 14 minus 11 is 3. Okay? But if you had a bunch of these to do, then we would want to use stone. Right? So what I want you to do is in your calculator, in the mainstream of your calculator, put 2x minus 11 in your calculator. All right, x is up in the top. Top left. Get it? Right there. That's the x button.
Yep, that's the enter score.
Okay. All right, and then press enter, and you're going to get a number, but we're not worried about that number yet because you've already have x. So you have 2x minus 11 in your calculator. Now, we're going to take 5 Press 5, stow, and press X, and then enter. 5, stow, X, enter, and you should see it say 5 again. Everybody got that? Okay, and everybody got the 5. Anybody not get the 5? Okay, now, we're going to go back to this. We're going to press the second button, and then enter. That's going to take us back to stow, and then we're going to go second, enter again, and you're going to see 2x minus 11. All right, what we're doing is we're going back to the screen on the previous time you pressed enter, but now x is 5, so when you press enter, you're going to have 10 minus 11, negative 1. Okay? So here's what I want you to do. I want to know this. What is f of 24? Store 24. 24, stow, x, enter, second enter, second enter. 37. Okay, now, that is pretty simple, but what would happen if my equation had been this? In that case, it would make sense to store the value of x and let the calculator do the work. Right? So we're practicing it on problems that you probably could get the answer faster, but the skill is what I'm trying to teach. The skill is important because when we get to problems like now, and here's what we need to know. Is 2, 11 a point on that graph? Right? In order to get that, you have to replace the x with a 2 and see what you get. Now we can do that manually, but if I were doing it and I was tired, I'd put it in the calculator and store. So let's do 2 stow to x, 2 stow to x, and then put 3x squared minus 17x plus 2 in your calculator, and when you press enter, you'll get the y value when x is 2. Is it 11? What'd you get? And when you put 2 in that calculator in there, what'd you get? Negative 20. All right, so that means that 2, negative 20 is a point on the graph, and this is above the graph. Because I should be at negative 20, but I'm at 11, so I'm above the graph. Right? That's where we're headed. That's how we're going to begin to use these things and interpret. Okay, does it make sense? Question about that? All right, so I'm going to try to keep teaching you how to do stow, because that will be very helpful. And then the other thing that we did in that section right there is that we took the value of the x and compared it to what the y was. Whereas most of the time, what we did in Algebra 1 was that we were looking for the y that made the equation true, or we looked for the x that made the equation true. Okay? All right, so that's now constant. So now linear is x, y equals x. Now, y equals x, when x is 0, y is 0. What happens when x is 1? I'm here on the board here. What happens when x is 1? Y is 1. X is negative 4. Y is negative 4. Okay, so that puts the graph here. If this equation were changed and it said x minus 5, this whole thing would move down, and the 0 would now be at minus 5. Because 0 minus 5 is negative 5. And so the whole graph moves down. This is absolute value. It's this graph with this section on the negative side made positive, because absolute value does that, doesn't it? Doesn't absolute value make negatives into positives? So this part here is going up instead of continuing down. This part of the graph is exactly like that part of the graph. All right, this is what we did some in algebra 1, we do a lot in algebra 2. All right, x squared. Now, what happens when x is 0? Y is 0. When x is 1, y is 1. When x is 2, y is 4. So, if I know this center part that's called the vertex, if I go over 1, I go up 1. If I go over 2, I go up 4. If I go over 3, I go up 9. Because it's square. It's square. If I go back 1, negative 1, I go up 1. Because 1, negative 1 times negative. If I go negative 2, I go up 4, negative 3, up 9. That's what produces that graph. And when you're negative 4, you're up 16, you're already off the graph in most cases. All right? So that'll be that. Square root, what's the square root of 0? 0 times 0. Square root of 1 is 1. Square root of 4 is 2, so this will be over 4 up 2, over 3 up 9. Oh, wait a minute, that's this graph. Turn it on the side. But what happened to this? What happened to this part of it? Because when I rotate this 90 degrees, I get this half. Why isn't this half here?
Because they're positive numbers.
Wait a minute. Can you take this?
Square root is half of.
Can you take this? No. Can you take the square root of a negative number? No. So the negative part doesn't have a square root. It's imaginary. That's why there's only this part. All right. Cube. What is negative 2 times negative 2 times negative 2? It's negative 8. So in a cube, you have both parts. But this part comes down, and this part would have gone up, but because it's negative, it goes down. Cube root, does it look like this sideways?
Yes.
Okay. And then this irrational one, this we won't get into, but it's important to know. Now, those right there, when I taught in Hall County, 8th grade, that was 8th grade. To memorize what they look like and what their names were. So that by the time you got into Algebra 2, none of that was new. And I think they've stopped doing that. And so what these graphs look like and the equations from which they come, you're learning for the first time. Whereas back 20 years ago, this was a simple 8th grade skill because it was something you memorized. It was what it was. Right? So if I ask you, what does an absolute value equation look like? The answer I was looking for was the V. What does a quadratic equation look like? A U. Right? What does a constant look like? A flat line. Because what's a linear graph look like? A line or a slanted line, right? Okay, so the difference between a constant graph and a linear graph was the constant was flat. Y was only worth one number. Okay, and then the square root is a quadratic turned on its side, and why did we lose the bottom part of the quadratic? When we took the quadratic and rotated it 90 degrees, but why did we lose the bottom part?
It can't be negative.
Because you can't take the square root of a negative number, right? And so that's how those things are all related, okay? Now, what you're going to do is what's right here. Okay, and I've got this on your handout. So if x is these values, then what happens when you square it? What value goes in here?
9.
9. And what value goes there? 4. All right? And it doesn't matter. All right, suppose that I had given you this. I'm going to change this to 3x plus 2. All right, suppose I'd given you this. All right, when x is 3, what does this become?
11.
9 plus 2, this becomes 11. All right? And so you can make these T-charts all day long. Right? The one that you're supposed to know is this one here. You're supposed to know that if you're, no matter where the vertex is, at the vertex there's no change, if I go 1 to the side, I'm over 1, up 1, over 2, up 4, over 3, up 9. Back 1, up 1, back 2, up 4, back 3, up 9. And you'll be able to draw a graph no matter where it is. Okay? What time? Oh my. 1 minute to spare. Okay, so I'll put all this up on your on the web page, but it's the same thing that's in, except that we will be 1 week ahead of time. This is week 4 in the on the website, and the reason is that when we get to a place and we're doing quadratics, I want to slow down so that everybody makes sense.
I was going to say, can we get an extra week off?
What?
I was going to say, can we get an extra week off?
No, but what is going to happen, when we start plotting quadratic equations, it takes more than a week.
Right.
And I want to take more than 1 hour to go over it with you. So in order to do that, we've already made it up. I mean, how hard was the homework the last 2 weeks? We could have probably done all of it in 1 week. Because you guys are that good. So. All right? Okay. All right. Okay, so if you would you turn that, press the button, turn it off.